Let's take a look at an example dealing with the law of conservation of momentum. And as a reminder, the law of conservation of momentum tells us that in a collision, the momentum is conserved or saved. It's just like the law of conservation of energy. You can't create energy or destroy energy, it's transferred. So in any collision, our starting momentum will always be the same as our ending momentum. It's transferred from one object to another. So here we have an example where a satellite is orbiting planet Earth and a meteor crashes into our satellite. So we're going to take a look at the momentum before and after the collision. I give you some information here, like the mass of the satellite and the meteor, and the starting velocities or speeds. So let's try to calculate this. First, we know that our mass is 500 kilograms, which is right here. Our starting velocity is 10,000 meters per second, which is really fast. And it makes sense because the satellite is orbiting all the way around Earth, so it's going very fast. The mass of our meteor from our diagram is 6,000 kilograms, which is huge and makes sense because meteors can be very large. And it's traveling at a speed of 2,000 meters per second. Still very fast, but not as fast as our satellite. So to calculate momentum, our formula is momentum, little p, is equal to the mass of an object multiplied by the velocity times the velocity. Here, the satellite, P equals m times v, has a mass of 500 kilograms. It has a speed or a velocity of 10,000 meters per second. And if we were to use a calculator, which is totally fine, we would find that our momentum would be 5 million kilograms meters per second. Now think about that. 5 million, it's a very large number. That makes sense. It would take a lot of energy to slow down or to stop the momentum of a satellite. So these numbers are going to be very large today. Similarly, we could do the same thing. P equals m times v, 6,000 times 2,000. And we would find that the momentum of our satellite is 12 million kilograms meters per second. So in total, if I added these two numbers together, before, we would have a momentum, a total momentum of 17 million kilograms meters per second. Based on the law of conservation of momentum, we would predict that at the end, our total should be the same. So let's hope that if we're doing our problem right and doing our math right, that these two numbers should be the same. All right, now they've collided. Remember, momentum is transferred just like energy. So our satellite's going to bounce off going one speed in one direction. Our meteor will also bounce off and going a different speed in a different direction. Mass will always stay the same, okay? So I give you a little bit more information here to help solve this. I tell you now that after they collide, the satellite speeds up. It goes from 10,000 to 13,000 meters per second. It still has a 500 kilogram mass, but it's increased its velocity. Same thing with our meteor. It still has a 6,000 kilogram mass, but it's actually slowed down after it's collided with our satellite. So here, if we solve for our momentum, mass times velocity, 500 times 13,000 would give us 6,500,000 kilograms meters per second. Same thing here. Momentum is equal to mass times velocity. Plug these numbers in. 6,000 times 1,750 meters per second would give me a momentum of 10,500,000 kilograms meters per second. So if we were to add these two numbers together, we would find that our total at the end after the collision is 17 million kilograms meters per second. So we saw in this example, even something as earthly as a car crash to as cosmic as a satellite crashing into a meteor, momentum from start to finish, using our math, will always be the same. From start to finish, we saw that 17 million at the beginning, 17 million at the end. The law of conservation of momentum.